determine the appropriate electrical setup for powering 8 400-watt metal halide lamps, several factors need to be considered, including the total load, current draw, and appropriate circuit protection. Let's begin with the calculations. The total load is determined by multiplying the number of lamps by the wattage per lamp. In this case, 8 lamps multiplied by 400 watts per lamp equals 3,200 watts. Next, we need to calculate the current draw at 120 volts. This is done by dividing the total wattage by the voltage. Therefore, 3,200 watts divided by 120 volts equals 26.67 amps. Now let's discuss circuit protection. It was initially suggested to use 30 amp breakers. However, 30 amp breakers are typically rated for a maximum of 240 volts in residential applications. Given this particular circuit is designed to operate at 120 volts, and the voltage rating would be unsafe. Now, the question of fuse safety disconnect switches arises. 30 amp fuse safety disconnect switches are rated for 120 volts and would provide adequate protection for this scenario. Based on these calculations, the following is recommended. Firstly, install two 60 amp breakers in the outdoor 100 amp panel to serve the 8 lamps. Secondly, install two 30 amp fused safety disconnect switches in the 60 amp panel adjacent to the court to operate the lights. The rationale for these recommendations is as follows. The 60 amp breakers in the main panel provide adequate overcurrent protection for the circuit because 26.67 amps is less than 60 amps. The 30 amp fuse safety disconnect switches provide local protection for the lamps and allow for easy isolation of the circuit for maintenance or troubleshooting. This configuration meets the vendor's requirement for a maximum current of 5.0 amps per lamp. Let's consider a few additional points. The wiring from the 100 amp panel to the 60 amp panel should be rated for at least 60 amps. This ensures that the wiring can safely handle the expected current load. The wiring from the 60 amp panel to the safety disconnect switches and lamps should be rated for at least 30 amps. This provides an additional layer of safety and ensures that the wiring can handle the current draw of the lamps. It is crucial that the installation be performed by a qualified electrician and inspected according to local electrical codes. This will ensure that the installation is safe and compliant with all applicable regulations. Choosing the correct wire gauge is essential for safety and optimal performance. Factors that influence wire gauge selection include ampacity, which is the current carrying capacity of a wire, distance or the length of the wire run, voltage drop, which is the decrease in voltage along the wire, and temperature rating, which is the maximum temperature the wire can withstand. Using a wire gauge that is too small can lead to overheating, insulation damage, and even fire hazards. Voltage drop can cause equipment to malfunction or operate inefficiently. Local electrical codes such as the National Electrical Code, or NEC, specify minimum wire gauge requirements based on ampacity and other factors. Consulting NEC Table 310.15b16 is crucial for determining the appropriate wire gauge for a specific application. For example, if the circuit breaker is rated for 60 amps and the wire is type THHN copper with a temperature rating of 75 degrees Celsius, the minimum wire gauge required would be number 6 American wire gauge, or OAK. If the distance between the panel and the load is significant, voltage drop calculations should be performed to ensure that the voltage at the load is within acceptable limits. Several online voltage drop calculators are available. These calculators take into account wire gauge, distance, current, and voltage to determine the voltage drop percentage. A voltage drop of more than 3% is generally considered unacceptable and may require increasing the wire gauge. The type of conduit used to protect the wiring also plays a role in the overall safety and performance of the electrical system. Common types of conduit include rigid metal conduit, or RMC, intermediate metal conduit, or IMC, electrical metallic tubing, or flexible metal conduit, or FMC, and rigid polyvinyl chloride, or PVC conduit. RMC and IMC are typically used for heavy-duty applications where physical protection is required. EMT is a lighter weight option that is commonly used for indoor applications. FNC is used for short runs and for connecting equipment that may vibrate. PVC conduit is non-conductive and is often used for underground applications. The choice of conduit depends on the specific application and the environmental conditions. When installing conduit, it is important to follow all applicable codes and standards. This includes properly supporting the conduit, using the correct fittings, and ensuring that the conduit is properly grounded. Grounding is an essential safety measure that provides a path for fault current to flow back to the source, tripping the circuit breaker or fuse and preventing electrical shock. All metal conduit and equipment enclosures must be properly grounded. Grounding can be achieved by connecting the conduit and enclosures to a grounding electrode system such as a ground rod or a metal water pipe. Ground fault circuit interrupters, or GFCIs, are another important safety device that can help to prevent electrical shock. GFCIs monitor the current flowing in the circuit and trip the circuit breaker if a ground fault is detected. GFCIs are typically required in wet locations such as bathrooms and kitchens. When working with electrical systems, it is important to always follow safe work practices. This includes energizing the circuit before working on it, using properly insulated tools, and wearing appropriate personal protective equipment, or PPE, such as gloves and safety glasses. Always verify that the circuit is energized before working on it. This can be done by using a voltage tester to check for the presence of voltage. Lockout-tagout procedures should be followed to prevent the circuit from being accidentally re-energized while work is in progress. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician to do the work. Attempting to perform electrical work without the proper training and experience can be dangerous and can result in serious injury or death. Always consult local electrical codes and regulations before starting any electrical project. These codes and regulations are designed to ensure the safety of people and property. Failure to comply with these codes and regulations can result in fines and other penalties. In addition to the points already mentioned, it's worthwhile elaborating on the selection of appropriate overcurrent protection devices. Fuses and circuit breakers serve the same fundamental purpose to protect electrical circuits from overcurrent conditions, but they operate and are applied differently. Fuses are single-use devices that melt and interrupt the circuit when the current exceeds a predetermined level. They are generally faster acting than circuit breakers, making them suitable for protecting sensitive electronic equipment. Fuses are available in a wide range of ampere ratings and time delay characteristics. Circuit breakers are reusable devices that trip and interrupt the circuit when an overcurrent condition occurs. They can be reset manually after the fault has been cleared. Circuit breakers are commonly used in residential and commercial electrical systems. Circuit breakers are also available in a variety of ampere ratings and trip characteristics. When selecting overcurrent protection devices, it is important to consider the following factors. Firstly, the ampere rating of the circuit. Secondly, the type of load being protected. Thirdly, the interrupting rating of the device. And fourthly, the time delay characteristics. The ampere rating of the circuit should match the ampere rating of the overcurrent protection device. The type of load being protected will influence the choice of time delay characteristics. For example, motor circuits typically require time delay fuses or circuit breakers to allow for the inrush current that occurs when the motor starts. The interrupting rating of the device should be high enough to safely interrupt the maximum fault current that could occur at the installation location. Another key aspect of electrical installations is understanding and mitigating harmonic distortion. Harmonic distortion is the presence of harmonic currents and voltages in an electrical system. Harmonics are multiples of the fundamental frequency, which is typically 60 Hz in the United States. Harmonic distortion can be caused by nonlinear loads, such as electronic ballasts, variable frequency drives, and uninterruptible power supplies. Harmonic distortion can have several negative effects on electrical systems, including firstly, increased heating of conductors and transformers. Secondly, misoperation of protective devices. Thirdly, interference with communication equipment. And fourthly, reduced power factor. To mitigate harmonic distortion, several techniques can be used, including firstly, using harmonic filters. Secondly, using phase-shifting transformers. Thirdly, using line reactors. And fourthly, using power factor correction capacitors. Harmonic filters are designed to block harmonic currents from flowing in the electrical system. Phase-shifting transformers can be used to cancel out certain harmonics. Line reactors can be used to reduce the harmonic current generated by nonlinear loads. Power factor correction capacitors can be used to improve the power factor of the electrical system, which can also help to reduce harmonic distortion. Regular maintenance and inspection are crucial for ensuring the safety and reliability of electrical systems. Maintenance tasks should include firstly, inspecting wiring and connections for damage or corrosion, secondly, testing overcurrent protection devices, thirdly, cleaning electrical equipment, and fourthly, tightening connections. Inspections should be performed by qualified personnel using appropriate test equipment. Infrared thermography can be used to detect hot spots in electrical equipment, which can indicate loose connections or overloaded circuits. Power quality monitoring can be used to identify harmonic distortion and other power quality problems. Any deficiencies identified during maintenance or inspection should be corrected promptly to prevent further damage or safety hazards. Staying current with the latest electrical codes and standards is also essential for ensuring the safety and compliance of electrical installations. Electrical codes and standards are constantly being updated to reflect new technologies and best practices. It is important to stay informed of these changes and to ensure that electrical installations are designed and installed in accordance with the latest requirements. Professional organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, offer a variety of resources for staying current with electrical codes and standards, including training courses, publications, and online forums. In conclusion, powering metal halide lamps requires careful consideration of several factors, including load calculations, circuit protection, wiring, and safety measures. By following the recommendations outlined and consulting with a qualified electrician, you can ensure a safe and reliable installation. Additionally, understanding harmonic distortion, implementing mitigation techniques, and performing regular maintenance and inspections are crucial for maintaining the long-term health and performance of electrical systems. Remember that electrical work should always be performed by qualified personnel following all applicable codes and standards.